to talk about unconditional hardness of approximation.
Well said. Okay, so yeah, I switched on. Thank you. Okay, so let me start with the customary thanks to the organizers for inviting me to speak here. Saving on the travel expenses. I'm going to tell you about some work, which is, as it says, joint work with Albert Aterios. It's not, shall we say, in the center of the interests of this conference, but I will, I hope you'll find it interesting. And as with these things, I will spend a fair amount of time giving you some background information, but please feel free to interrupt, ask questions, because if I don't get to telling you about the results we proved, that's not so important. I'd like to get you to get something out of this talk. Okay. So this is actually work we did a couple of years ago. It's appeared in a paper in the Journal of Logic and Computation in about 2019 or 2020. And then I'll tell you a little bit about some follow-up work which a master's student of mine did more recently. Okay, so what's this about? What do I mean by hardness of approximation? I'll come to the unconditional a bit later. Let's start with hardness of approximation. Okay, this was working a moment ago. Okay, so yes. We're in the world of, let's say, NP optimization problems, right? So you're familiar with P versus NP. So here's the classic NP optimization problem. We call it max 3-sat. So we're given a Boolean formula, which is in 3CNF, conjunctive normal form, 3 literals per clause. The classic NP complete problem is determining whether the formula is satisfiable or not. Now, assume the formula is not satisfiable, but it has n variables, let's say, and m clauses. We want to know if it's unsatisfiable, how many of the clauses can we simultaneously satisfy, right? You given an assignment of truth values to the Boolean variables, you can't make all the clauses true simultaneously. It's unsatisfiable. How many can you make true simultaneously? That's the optimization problem, right? So let's say we write m star for the maximum number of clauses that can be simultaneously satisfied. And the problem is to determine the value of m star. Or the various algorithmic problems we can associate with this now. The fundamental one, the one people are actually interested in, who implement these constraint solvers, is actually find an assignment to values that maximizes the number of clauses that are satisfied. An apparently simpler problem is just determine the value of m star, how many can be simultaneously satisfied. Now, I said this is the one we're really interested in. So why go to this? Well, the point is, of course, because what we're doing is proving hardness. And if this is hard, then that one's hard, right? If you have an efficient algorithm for finding an assignment, then you can determine the value of m star easily. So if you prove that this one's hard, then it implies that you can't easily find an assignment. Even simpler one is to approximate the value of m star. What do I mean by approximate? So we have fixed some constant c between 0 and 1. And I ask you, well, you can't tell me the value of m star exactly. Can you give me a value of m prime which is guaranteed to be within a factor c of m star, right? So you want the algorithm to give you a value m prime, which is somewhere between c times m star and m star. Okay, that's what I call approximation of the optimum. So m star, I'll call the optimum value of phi. And the approximation problem is this last thing over here. So now, a bit of history. We've known for half a century now that satisfiability problem is NP complete, which means pinning down the value of m star exactly is not something we can do in polynomial time unless p equals np, right? This is because if we could pin down the value of m star, we could just check whether it's equals to m and therefore determine whether the formula is satisfiable, okay? So pinning down the value of m star is a hard problem. We've known this for 50 years. For about half that time, for about a quarter of a century, we've known it's also hard to approximate. Okay, so this is the PCP theorem. I I don't know how many of you are familiar with this, but it's, I mean, I was a graduate student when this was published, and it was big enough news that it made the New York Times, okay? The PCP theorem says that not only is the value, the optimum value of a formula hard to pin down exactly, it's hard to approximate within a constant factor. In particular, there is some constant, such that unless p equals np, you cannot approximate m star to within a constant within the factor c. Now, what is the constant? You look through the proof, and you can probably extract a lower bound on it of or of something like 0.99, right? It's hidden in the detail of the proof. It's really the existence proof, but kind of Johann Hofstad pinned this down pretty much precisely. He showed that unless p equals np, then for every epsilon, there's no polynomial time algorithm that will approximate the optimum value of a 3CNF formula to within 7/8 plus epsilon. Okay. Why is this pinning it down exactly? Because 7/8 you can trivially achieve. There is a polynomial time algorithm that will give you the a value guaranteed to be within 7/8 of m star, and the algorithm is utterly trivial. What's the algorithm? Give me any formula and I'll answer 7/8. Because any formula you can satisfy. So here's why 7/8. If you have a 3CNF, you look at a single clause, then there are 8 possible Boolean assignments to the 3 variables. 7 of them will make it true. Simple averaging argument says that in any CNF, 3CNF, there is some assignment that will make 7/8 of them true, right? So the answer, the exact answer is always within 7/8 and 1. So the algorithm which just answers 7/8 to every formula is a 7/8 approximation algorithm, by my definition. Okay? And Hofstad tells us that you can't do any better with any polynomial time algorithm unless p equals np. Okay? So you can't approximate anything other than the utterly trivial. Is hard to do. This is this is so what we mean by hardness of approximation are results of this form, which tell you that NP optimization problems are difficult to approximate unless P is different from NP. And now the first word in my title was unconditional. These are what I call conditional results because they're all based on a hypothesis, which is unproved, namely P is different from NP, which we believe. But so these we call conditional hardness of approximation results. Okay. Now, that's max 3 sat. There's sort of a bit more of a general theory around these NP optimization problems. Papadimitriou and Yannakakis defined a class of optimization problems that they call max SNP. SNP stands for strict NP. I won't give you the exact definition. It's defined in syntactic terms. You can define problems by expressions of existential second-order logic, and the syntactic form of the expression is what defines this class. And they showed that for every problem in max NP, there is some constant to within which you can approximate. I mean, these are optimization problems. So every problem in this class has a constant factor approximation. Note there are problems, NP optimization problems, which are not in max SNP, for which you can show hardness, that it's hard to approximate within any constant factor. These ones, at least we know there is some constant factor approximation. But you can then define a notion of completeness under certain approximation preserving reductions. And for complete problems, max 3 sat is an example. And we know there is some constant beyond which you can't approximate, right? So for max 3 sat, we know it pretty precisely. You can approximate to within 7/8. You can't approximate to anything more than that. And so it's a consequence of the PCP theorem that for any max SNP complete problem, there is some constant C beyond which you can't approximate. There's a hardness bound, right? There are constant factor approximation algorithms, but they stop at some point. Beyond that, it's NP hard to come up with an approximation. And so it's been, for the last 20 years, shall we say, an ongoing big body of work for various problems with max SNP, identifying the actual hardness of approximation constant. Okay, let me give you some examples. Max 3 XOR is another interesting one. What do I mean by Max 3 XOR? You're given a Boolean formula. Again, conjunction of clauses. Each clause has 3 literals, but instead of a disjunction, we have exclusive OR inside the clause. Okay? That's what we call a Max 3 XOR. Now, again, I'll write n for the number of variables and m for the number of clauses, and m star for the maximum number that you can simultaneously satisfy. Now here, the original decision problem, the satisfiability problem, is not hard. If I give you such a formula, determining whether the whole thing is satisfiable or not, I can do. Why is that? Right? So determining whether m star is m, namely the formula is satisfiable. Well, what is a conjunction of clauses? Now, because it's exclusive OR, I can look at each clause as an equation over the 2-element field, right? Exclusive OR is simply addition in the 2-element field. And so I'm solving a system of equations. I want to know if the whole system is satisfiable. I use Gaussian elimination, and that's a polynomial-time algorithm. But that's determining the boundary between satisfiable and unsatisfiable. But if it is unsatisfiable, finding out how many I can simultaneously satisfy is hard. Determining the exact value is max SNP complete. So there is some constant beyond which I can't approximate this. And again, we know the constant exactly. Hofstad did this in the same paper. You can't do better than a half. Okay. And again, the half is trivial because exactly for the same reason that 7/8 of the assignments will satisfy a clause. If it's exclusive OR, half of the 8 assignments of truth values to a clause will satisfy it. Same argument shows you. So that the half is trivial. Doing anything better than a half is hard. Okay. A problem of a slightly different character. Here's another classic NP-complete problem. You have a graph. A vertex cover in a graph is a set of vertices such that every edge has at least one endpoint in the set. Okay, so all edges are covered by the set. The classic optimization problem is find the minimum size vertex cover. We call that VCG, the size of the smallest vertex cover. We have a hardness of approximation. This is the best we know. It's relatively recent, and it's the result of a long progression of results, and there are a lot of difficult results to prove. So there's no polynomial-time algorithm that can approximate this up to a factor of square root of 2. Before my problems were maximization problems, so my approximation factors were less than 1. I'm now talking about a minimization problem, find the smallest size vertex cover. So my approximation factor is bigger than 1. If you like to be consistent, you can just take the inverse, right? So the point is, there's no algorithm, unless P equals NP, there's no polynomial-time algorithm that will, in a graph, tell you the size of a vertex cover within a factor of the square root of 2. Factor of 2 we can do. That's easy. Okay. Some simple greedy algorithm will achieve the factor of 2, right? You just pick an edge, any edge so far for which both endpoints are not in your set, pick one of the endpoints, stick it in your set, and proceed until you've covered all edges. This will find you a vertex cover guaranteed to be no more than double the size of the minimum. So factor of 2 we can achieve. Factor of square root of 2 we can't. Where is the boundary? We don't know. The conjecture is that you can't do anything better than 2, right? So the conjecture is that unless P equals NP, there is no 2 minus epsilon approximation algorithm for any epsilon, but the best lower bound we have is square root of 2. Okay, so this is this remains open. Okay, so how are these hardness results proved? This is just a bit of terminology. I'll say that a formula is C satisfiable if you can simultaneously satisfy a C fraction of the total number of clauses. Okay. So what the proof of the PCP theorem does is it's really just a reduction from 3-sat to itself, which maps a satisfiable formula to a satisfiable formula, and at the same time takes any unsatisfiable formula to one that's not even C-satisfiable. So it really, what the proof of the PCP theorem is, I mean, they call this kind of, at the time it was called holographic proofs. I mean, I think the term PCP is stuck for probabilistically checkable proof. But essentially, it multiplies the number of clauses in your, in your CNF formula, which amplifies the unsatisfiability. So anything that is unsatisfiable becomes sort of much more unsatisfiable. You can't satisfy more than a C fraction. But anything satisfiable is still mapped to something that's satisfiable. And there's a polynomial time reduction. The consequence is that if you have any collection of formulas which includes all the satisfiable ones, but excludes the ones which are not even C-satisfiable, then that class must be NP hard to decide, right? Because you have, this thing gives you a reduction from 3-sat, which we know is NP complete, to this class. And if this thing is hard to decide, then that means you cannot approximate in a polynomial time the value m star to within a factor of C, because if you would, you could decide this, such a class, some such class, right? You would just, for any formula, determine the value of m star, and see whether you're guaranteed to be within a factor C, or you have an algorithm which gives you the value of m star to within a factor of C, and so you can, that algorithm, you take the decision problem, which, takes that algorithm, and if it says you're within C of M, you accept. If it says you're not within C of M, you reject. That will decide some class which separates the satisfiable formulas from the ones that are not C-satisfiable. And what the PCP theorem tells us that there is the class of satisfiable formulas is not efficiently separable from the ones that are not C-satisfiable, right? So at the core of the proof is it's a reduction. It's a polynomial time reduction, which just amplifies the unsatisfiability. And then once you've got a gap, this factor of C gap, you can amplify it with further reductions, and this is what Hofstad does. And he finds ways of increasing this gap to 1 versus 7/8. And in the case of 3 XOR, the result of Hofstad is that there's no efficient separation between those formulas which are 1 minus epsilon satisfiable and those that are not half plus epsilon satisfiable. Note, you can't put a 1 here rather than 1 minus epsilon, because for XOR, deciding satisfiability is doable in polynomial time, right? So this, I mean, in the literature on hardness of approximation, that's called the completeness factor, and that's called the soundness factor, right? So you can't improve this to what's called perfect completeness. You can't replace the 1 minus epsilon by 1. But in the case of 3-sat, you can, right? And so, Hofstad sort of really gives a reduction from 3 XOR to 3-sat to get the optimal separation or hardness result for 3-sat. That is, any class of CNF formulas that includes the satisfiable ones, but exclude those that are not 7/8 plus epsilon satisfiable, is NP hard to decide. Okay, that's really, oh, no, okay, I've got a bit more. So what about vertex cover? So you pick your favorite textbook on complexity theory, and it might include a proof of the NP completeness of vertex cover, usually by a reduction from 3-sat, right? You'll find this in Sipsa's book and Papadimitri's complexity book. What it does is, it says, if you start with a 3CNF formula, we can turn it into a graph, which typically has 3M vertices. You put a little triangle for each clause in your formula, and you then show that it has a vertex cover, which includes, any vertex cover must include 2 vertices from each triangle. So the smallest vertex cover is really 2 times the number of clauses you can simultaneously satisfy, right? That's the in the classic proof of NP completeness. What does this tell us about hardness of approximation? Well, immediately we get something, because if you look at what we know about 3-sat, that we can't separate satisfiable from 7/8 plus epsilon satisfiable, then this translates into showing that you can't separate graphs where the smallest vertex cover is less than 7/12 plus epsilon of the number of vertices, right? This is basically there's a factor of 2/3 there, which gets multiplied by the 7/8. You can't separate those from those which are, well, the satisfiable ones translate into ones where the vertex cover is at least 2/3. So taking the ratio of those two, we show this immediately tells us that you can't approximate vertex cover to within a factor better than 8/7. Start with 3 XOR instead of 3-sat, and Hofstade's inseparability of half plus epsilon versus 1 minus epsilon. And you can improve that 8/7 to 7/6. For many years, the best known bound was about 1.36. And as I said, Kottminzer-Safra, about 3 or 4 years ago, in a major breakthrough, improved it to square root of 2. And again, if you look at these proofs, they are really just sophisticated reductions, right? They are ultimately codings of satisfiability into graphs with very sophisticated gadgets. But that's where we are. Okay, so this is I've taken 20 odd minutes giving you background on hardness of approximation. Now I want to tell you something about something completely different. Because the thing I've been working with is fixed point logic with counting. This is a formalism for writing down definitions of problems, which is sort of extension of first order logic with recursion and a mechanism for counting. I'm not going to give you a more precise definition than this. It was first proposed by Neil Immerman back in 1980s as a formalism in which we could express polynomial time problems and nothing else. Even conjectured that you could do all polynomial time problems. That turns out not to be the case. So, in a paper by Safra and Immerman, famous paper, they showed that there are graph properties which are polynomial time decidable, but not in FPC. But it still defines a large and natural fragment of P, and it was worthy of study in its own right. And here's my spoiler. So my unconditional hardness of approximation results are of the form that without any assumption about P versus NP, you cannot approximate these NP optimization problems in FPC. Okay, so that's the spoiler. But let me tell you a little bit more about FPC. The point is that many powerful polynomial time algorithms can be expressed in FPC, but at the same time, like this example shows, we have unconditional lower bounds. We actually can prove true impossibility results without making the hypothesis that P is different from NP. Okay, this is just a little digression. I haven't given you the definition of FPC, but I'm going to give you a completely different characterization because I like this because it shows that we're dealing with something fairly natural. I said it's definability in a formalism. It has a purely combinatorial circuit characterization as well. Very quickly. So if you have a Boolean function, right, which takes n01 values to 01 values, we say it's symmetric if it's invariant under all permutations of its inputs. In other words, it just counts the numbers of zeros and ones and takes some decision on the numbers. I'll call a function graph symmetric if it basically takes the adjacency matrix of an undirected graph, right? But is deciding some property of the graph rather than of the matrix. In other words, what's the adjacency matrix of a graph? For each potential edge, it tells you whether the edge is present or absent on an n vertex graph, right? N choose 2 are the 2 element sets on n vertices. So 0, 1 to the n choose 2 is a graph, right? It tells you for each potential edge whether it's present or absent. And the function gives you some decision property, right? Like it has a vertex cover of size 5 or it doesn't. But if it's deciding a property of the graph, then if you permute the vertices, it shouldn't change the value of the function. So we say this function is graph invariant if it's invariant under the natural action of the symmetric group Sn on the inputs n squared. We say that a circuit for computing this Boolean function is symmetric if, when you apply this permutation to the inputs, it extends to an automorphism of the whole circuit. So you can just permute the gates of the circuit, it looks the same. In other words, the circuit really doesn't do anything different if you reorder the vertices of your graph. Now, what is a circuit? A circuit, in each function, you're computing something like an AND or an or some counting property of the inputs. So I'll be generous and I will allow any symmetric function at the gates of the circuit. And then it turns out that FPC is exactly those properties which are decidable by uniform families of symmetric circuits in this sense. Okay. So what this is saying is that when we say that this is not all of polynomial time, what we're really saying is that things which the reason is that in polynomial time, you have symmetry breaking algorithms which decide actual properties of graphs, but crucially in the course of the algorithm, you have to do different things depending upon the order of the vertices that come in the input. Okay, so I just like this characterization because it gets away from the, I said it had to do with first order logic and recursion and counting, but we can characterize it purely combinatorially. Okay. FPC has been studied for many years. And in a sense, if you come up with a polynomial time algorithm for deciding something on graphs, if it's obviously polynomial time, you're probably in FPC, right? In the sense that the usual things you can do, recurse over the graph, count various numbers of things, etc. They all turn out to be in FPC. Many things which are not obviously polynomial time, but highly non-trivially proved to be polynomial time, also turn out to be expressible in FPC. And in here, the kind of poster child of this program is Grove's rather monumental result that any property of graphs which is closed under taking minors and decidable, or any property of graphs which is decidable in polynomial time over a class of graphs closed under taking minors is an FPC. This reproduces a whole lot of this Robertson-Seymour graph structure theory inside this kind of model of symmetric computation. Worth mentioning. Another thing I wanted to tell you, we kind of showed that various linear programming methods based on the ellipsoid method for solving linear programs are expressible in FPC, so you can express things like finding the maximum matching in a graph, et cetera, et cetera. These are, I just wanted to say, linear programming, the Robertson-Seymour results maximum matching. I mentioned these because for each of these, the first polynomial time algorithm was a major result, right? When it was first proved that matching can be done in polynomial time by Edmonds in the 60s, this was a significant result. The fact that linear programming can be done in polynomial time, first proved by Kacyan in late 70s, early 80s, was a major breakthrough. The Robertson-Seymour graph structure theory, of course, was a major breakthrough of the 1990s. It turns out all of these are in FPC, yet there are polynomial time algorithms which you can't do in FPC. In particular, 3 XOR. Deciding the satisfiability of a 3 XOR formula, you can't do. So I mentioned Gaussian elimination. Gaussian elimination is an algorithm you can't implement symmetrically, it turns out. Okay. That's what FPC is. Now I can state our results. These are unconditional hardness of approximation results. You can't approximate the optimum value of a 3CNF formula to better than 7/8 in FPC unconditionally, right? No hypothesis that P is different from NP. So even if P were to be equal to NP, shall we say, there is no symmetric algorithm that can approximate SAT to within a factor of better than 7/8. And the same for XOR, we reproduce essentially the hardness of approximation results for something strictly weaker than P, but dropping the hypothesis that P is different from NP. And for vertex cover, we reproduce the 1.36. I think we can do the square root of 2 as well, but that's kind of, at the time we did this, the Court-Minzer-Safra result was brand new, and we didn't really delve into the details of that proof to see if it could be done. So these are unconditional hardness of approximation results. And I'll tell you a little bit about what is involved in proving them. So the formulation of FPC we were working with was, I said, fixed point logic with counting, which I didn't define for you. Let me give you something a little bit simpler, maybe. Start with first order logic that you're familiar with. So when I say first order logic, what I mean is you're writing down formulas, let's say in the language of graphs, if we're talking about graph properties. So so you want to say that there is a vertex cover of size 5. You would say there exists x1 up to x5 for every y and z. If there's an edge between y and z, then then one of the endpoints is among x1 through x5, right? This says that there is a vertex cover of size 5. Okay, so this is what I mean by first order logic in the language of graphs. I'm going to extend my logic in a way by allowing quantifiers, not just existential and universal, but I can say that there exists at least exactly there exists at least I elements x such that phi. That doesn't seem to be adding anything, because obviously I could just use I quantifiers to do this. But this is a limitation, because I'm limiting myself to at most k distinct variables to get ck. Why this bizarre thing of extending in one sense and then restricting? This counting k's turns out to be a very useful resource for measuring how difficult it is to express something. So we say two structures are k equivalent if there is no sentence of this logic which distinguishes A from B. And the thing about FPC is you can show that for every sentence of FPC, there is some constant k, so that if two things are indistinguishable, then they're not separated by the sentence. Okay. So this constant, the point is k depends only on phi and not on the size of these structures. Okay. So let me put it this way. So again, to prove that something is not definable in FPC, you simply show that the thing you have a collection of finite structures. You show that it's not invariant under this equivalence relation for any fixed k. It follows that it's not definable in FPC. And how do you show that two things are equivalent with respect to ck? We express this in terms of a game. We have a pair of structures, A and B. And the game is played. That's the game board. We have two players called spoiler and duplicator. Think of it this way. Spoiler is trying to demonstrate that these two structures are different. Duplicator is trying to pretend they're the same. And spoiler has a resource limitation given by k pebbles, which spoiler can place on the elements of the structure. At each move, spoiler chooses a pair of pebbles, AI and BI. Duplicator gives a bijection between the two structures. If there's no bijection, then the two structures are different. There's nothing to prove. And the bijection has to be that for pebbles other than this one, which are already, these pebbles sit on chosen elements of A and B. For those other than the pair that's moving, the bijection must respect the current pebble placement. And then duplicator chooses an element of A. The element AI goes on A, and BI goes on its image under this bijection. And then the game carries on for another move. Spoiler removes another pair of pebbles from the board. Duplicator gives a bijection. Spoiler places them, etc. If at any point the map induced, these k-public positions induce a substructure of A and a substructure of B. If the map is not a partial isomorphism, Duplicator has lost the game. The structures are different, and Spoiler has demonstrated it. And you can show that Duplicator has a strategy to play forever if and only if the structures can't be distinguished. This is, okay, one direction is fairly easy, and that's the direction we're really interested in. If there is a formula which is true in A and false in B, that formula really just describes a winning strategy for Duplicator. In the bijection, whenever you have a quantifier in the formula which is true in one structure and not the other, which means there is some count, there exists Ix, which will be different in A and B. So Duplicator's bijection will violate this condition at some point, and Spoiler just picks the witness of the violation and carries on now with a smaller subformula. Bit of a hand-wavy proof, but that's the argument. Okay. So now we have a collection of structures. My structures are finite structures always. So it's a collection of finite structures like finite graphs. I define its counting width to be this function, which for n gives the smallest value of k, says that when you restrict to structures with at most n elements, it's closed under k equivalence. So note, you can always distinguish two structures of size n with n variables. So this thing is mu c of n is always less than or equal to n. But so we're interested in how it grows with n. The point is that, from what I told you before, anything that's doable in FPC has counting width bounded by a constant. But for something like 3-SAT and 3-XOR, we can show that their counting width grows linearly, and therefore they're not definable in FPC. Okay, this is for the decision problems. This was kind of known before our work. So what we're doing for when we prove hardness of approximation, we're showing not just that okay. So how do you show that 3-SAT has counting with omega n? Typically, you come up with a satisfiable instance and an unsatisfiable instance, where the number of variables is some linearly growing function of n, and you show, or linearly growing function of k, if you will, and you show that Duplicator has a winning strategy with k pebbles on this pair of instances. That's what proves that the counting width grows linearly. Okay, and typically when you do these, your proofs, these things are sort of minimally different. You have a satisfiable and an unsatisfiable instance. You typically get them by taking a satisfiable one and making a small tweak to make it unsatisfiable, so that they very much look the same, and it's very hard for Spoiler to pin down the difference between them. In order to do our results, we want to show, for instance, that in any class, if you have any class of 3-XOR formulas, which includes satisfiable ones and excludes those that are not half plus epsilon satisfiable, then it still has counting width growing. Well, we need it unbounded, but we actually get a linear lower bound. And I note perfect completeness. So this is slightly better than Hofstade's conditional hardness of approximation, in that we're able to replace 1 minus epsilon with 1, because while satisfiability of 3-XOR is decidable in polynomial time, it's not in FPC. Okay. And then we get a reduction to get the gap for 3-SAT. And this is our unconditional gap result. So any class of formulas which includes the satisfiable ones and excludes those that are no more than 7/8 satisfiable has unbounded counting width. So in a sense, we call this new challenges for Duplicator. That was the title of our paper, because we're really giving winning strategies for Duplicator in these bijection games, but now playing on pairs of instances which are not just minimally different, but significantly different, because one is satisfiable and the other one is no more than 7/8 satisfiable. Okay, so you can't satisfy more than 7/8 of the clauses here, but you can satisfy all of them here, but they can't be distinguished by this by Spoiler in that bijection game we described. Okay. So unlike in the PCP theorem, which started with 3-SAT, we start with 3 XOR because that's where we had the FPC undefinability results before. And then we do it, extend it to 3-SAT and vertex cover. We do it by reductions. It's not sufficient to have polynomial-time reductions. We need our reductions to preserve this notion of counting width. So we give by reductions definable in first-order logic. I'm wondering how much to, yeah, but mainly we looked at the known reductions and showed that they could be doable in first-order logic. Let me see. I've still got about 15 minutes, right? Yeah, okay. So, I mean, I'm obviously not going to, well, let me give you some idea of how we get this initial gap. So we have a 3 XOR formula and a constant k. Now I'm going to define you a different game. This is not on a pair of structures. This is just on a single formula. And think of this, we have a challenger and a prover. The challenger is trying to demonstrate that the formula is inconsistent. It's unsatisfiable. And the prover is trying to pretend that it is. And again, challenger has limited resources. That's given by this constant k. Challenger chooses some collection of k clauses, looking for an inconsistency. Prover gives an assignment of values to the variable which satisfies all clauses in this set, right? But it's a subset of the total. Now, that's the stage 0. At each stage, challenger chooses another set of at most k clauses, and prover has to give an assignment of values to the variables, but with the condition that you can't change the values of any variable that appears in the intersection with the previous stage, right? So effectively, challenger is picking some subset of the clauses. Duplicator shows that they're all satisfiable, and then we move along slightly, right? And prover has to keep the assignment of variables to the clauses which are still in this set. But if new variables appear, the prover is free to choose a new assignment for them. So essentially, challenger is trying to find the inconsistency with a window of fixed size k, moving it around, and prover is constantly finding values to the variables which keep everything in the window consistent. Okay. If prover has a strategy to play forever, we say that the formula is k locally consistent, right? Because not just every k size subset is consistent, but you can sort of move this k size subset around while keeping a consistent picture of it. Okay. I've already said this, so we think of a formula of 3 XOR as a system of equations over Z2. Say, right, the 2-element field or the 2-element group, whichever way you want to think of it. And from such a system, we lift to a system we call CFI-phi. The lift, okay, is defined by replacing every variable by 2 new variables, replacing any variable x with x0 and x1, and replacing each such equation by 8 equations. So here we have the 8 ways we could replace these 3 variables by their new companions. And on the right-hand side, we take the sum of those 3 indices and add it to the right-hand side over there. Okay. So each such equation gives rise to a system of 8 equations. And note that in these 8 equations, there will always be 4 with 0 on the right-hand side and 4 with 1 on the right-hand side, no matter what the value of b was. We also define the homogeneous companion of phi to be the one where you replace b by 0 everywhere. Now, note that the homogeneous companion is always satisfiable, right? If the homogeneous system of equations is satisfiable. But what we show is that if the formula is k locally consistent, then once you perform this lift, the lift of phi 0 is not homogeneous. It has an equal number of zeros and ones on the right-hand side, but it's still satisfiable. But it is indistinguishable in the bijection game now from the lift of phi. Okay. And so now what we need to do is choose phi so that it is k locally consistent. But once you lift it, no more than half or half plus epsilon of the equations are satisfiable. And here everything is satisfiable. So that gives us our proof. So how do you choose phi to be k locally consistent, right? But still have, say, no more than half satisfiable. And that's actually a randomized construction. So we have a set of n variables. You choose uniformly at random a collection of m subsets of size 3. And you can show that with a high probability, you get a graph with good expansion properties. You construct a system of equations by choosing the right-hand side for each subset like this, again, by the toss of a coin. And you can show that with high probability, you can't, this is highly unsatisfiable. Okay. And the expansion properties are enough to guarantee that it's k locally consistent for growing values of k. And that's really the proof, right? So the actual construction is a randomized construction which proves the properties. Okay, and then we need to show that the lift doesn't destroy the highly unsatisfiable nature of it. And that's kind of it. Okay. I'm not going to go through much of this details. So we have, as I said, we have notion of reductions, which we perform sort of by defining by first order formulas rather than just polynomial time reductions. And they show, we show that they preserve this kind of counting width. And you get, okay. I've kind of told you the results for vertex cover, so I'll skip this bit. Let me just briefly introduce you to another problem, which is kind of neat. In the field of hardness of approximation, there's this rather famous conjecture known as the unique games conjecture. It's, in some sense, a stronger assumption than P is different from NP. It's conjecture to be true, but from it you can derive much much stronger hardness of approximation results than just from the condition that P is different from NP. So let me just tell you what the unique games conjecture is and what we're able to say about it. So suppose I have a graph, and every edge of the graph is labeled by a permutation of a set of size k. All right, so k is some integer constant. So for each edge in the graph, you have a permutation of k elements. And I ask the following question: can you color the vertices of the graph using these k colors in such a way that whenever you have an edge, the color at V is determined by the color of U by applying this permutation? Right? Now, this problem is easy to solve, right? Because what do? You just, in each connected component of the graph, pick a color for one vertex that kind of just, and propagate the constraint. That nature of permutation determines the color at every neighbor. Propagate. If ever you reach a contradiction, you know that the system is inconsistent. There is no coloring. If you reach no contradiction, it's colorable. Okay, this is just a generalization of the two coloring problem, which we know you can solve easily. Question is, if it's not colorable, how many of the edges can you simultaneously, how many of the constraints, which is the edges, can you simultaneously satisfy? That looks like a hard problem. And it looks like it's even hard to approximate. Okay, that's known as the unique games problem. I won't tell you where the name comes from, but so the unique games conjecture is that for any values of epsilon and delta in the range 0, so think of epsilon as being close to 0 and delta being close to 1. But any values, we can find a k so that the collection of instances which are delta satisfiable is not efficiently separable from those which fail to be epsilon satisfiable, right? So highly satisfiable between and highly unsatisfiable are hard to tell apart. Okay, that's the conjecture. The conjecture implies P is different from NP, so it's a stronger conjecture. But under this conjecture, okay, it's been proved for delta less than half. I say quote Minzer-Safra, this is the same result that gave the square root of 2 hardness of approximation for vertex cover. And in fact, the vertex cover hardness is a consequence of this. Okay. But if you could prove this unique games conjecture in general, it would imply hardness of approximation. I mentioned the 2 minus epsilon for vertex cover. Now you would get that as a consequence. You would get hardness about 0.878 for the max cut problem. And it would be optimal because we know of an algorithm that achieves this. Okay. So there are, so yes, and I mean, these are just 2 examples. There's a vast literature on consequences of the unique games conjecture. So what we would really like to do, we don't have this yet. This was our kind of goal when we launched on this, is a version of this again for FPC definability. So unconditionally, we think it might be possible to prove that for any epsilon and delta, those instances which are delta satisfiable and those which are not epsilon satisfiable cannot be separated by anything of bounded counting width. Okay. And this would give us the same kind of unconditional inapproximatability results, for max cut and vertex cover that are consequence of the unique games conjecture. And I just, as I said, I had a master's student, rather brilliant young man, who looked at this, and he gave us some partial results towards this. I'll just state the results. Essentially, you can't approximate the exact value of unique games within any constant. So he proves for any constant, you can't separate. There is a epsilon, so that you can't separate the epsilon and the C times epsilon instances of satisfiable instances of unique games with a class of bounded width. Okay, so that shows that you can't approximate the value of a k-level cover problem to within any constant. The trouble is that this epsilon goes down very quickly with the value of C, so delta is going down too. So what we don't have is getting delta close to 1, which is what we need for the unique games conjecture. On the other hand, keeping delta fixed at 1/2, you can get as it were, lower the soundness down to about 1/3. And he was able to show that you can't separate these with things of bounded counting width. They're really neat results. This was presented at the LIX conference last year. And what I find it really neat is that the proof is again by construction of instances where you play these spoiler duplicator games. But the instance construction is very different from the Cypher-Emmerman construction, which for the last 30 years has been the basis of all our FPC undefinability results. Okay, I'm at the end of my time, so I'll skip this bit. I mentioned to you that we know how to do linear programming in FPC, from which it kind of follows that our unconditional results show unconditionally that the standard linear programming or semi-definite programming methods that are used for approximation, unconditionally, they cannot achieve approximations, better than the 7/8 and so on, rather than just under the assumption that P is different from NP. Okay, so I'll get to my concluding slide. So we have a new way of studying inapproximability of NP optimization problems by showing they're undefinable in FPC. And I would say they show fundamental structural differences between the easy and the hard cases, which are not based on the hypothesis that P is different from NP. And they imply unconditional lower bounds for many of the actual algorithms people use for approximation, like linear programming, etc. What we haven't done is show an FPC undefinability result in a case where we don't know the NP hardness, okay, which I think would be neat to do. Okay, I'll stop there.
Okay, thank you. Do we have questions?
Did you look into sort of slightly stronger logics? Can you still get unconditional things, say for rank logic?
Okay, so rank logic is until last year we had no undefinability results for rank logic whatsoever, right? Because but Morris Lichter had a paper at LIX last year where he showed that certain things are certain polynomial time problems are not doable in rank logic. It's a rather hard paper to digest, but I mean, it gives us some methods. So potentially, yes, I mean, that's an avenue to explore, but at the moment we don't really have anything.
Okay.
Other questions?
Yeah.
Do you know anything about P versus FPC besides that they are different? I mean, any size difference or reduction?
I mean, obviously
or-
FPC is included in P.
Yeah.
We have examples of things which are in P but not FPC. So
I mean, for instance, like, do you have some sort of hardness with a different reduction, or I mean, does the reduction
right,
count
so,
or
so
not?
so certainly, okay, so in FPC, as I mentioned, there are various things we can do. You can show I mean, problems which are there are many problems which are P complete under, let's say, logarithmic space reductions or AC0 reductions, which are in FPC. It's just FPC is not closed under these reductions. That's why it doesn't do all of the P. You're saying size. I mean, there are things like you can show that there's sort of a class of graphs of, let's say, which includes almost all graphs. So asymptotically includes almost all graphs, on which every polynomial time problem is doable in FPC. So that's a sense in which it kind of approximates P pretty closely. But I don't know, yeah, I don't know of any other kind of general things which we could say about the size of these classes. Yeah.
You have more questions? So you just mentioned that there are problems, you know problems that are in P but not FPC.
Yes.
Can you just like name a few?
Well, I mentioned 3 XOR. It's just deciding the
yeah.
satisfiability of or solving systems of equations over a finite field.
Right.
Is the classic, yes.
Okay, we should check the online crowd.